Parvati, we can start.
Okay. Ma'am, shall we start?
Yeah, sure, we can start.
Okay. So good evening, everyone. Thank you for joining us at the closing ceremony of Singularity 2020, an online edition. This brings us to a conclusion to a week filled with exciting events, talks, and workshops. So on this occasion, we are honored to have with us a very special guest who I guess needs no introduction. We have Professor Rohini Godbole, Padma Shri 2019 recipient, and an honorary professor at the Center for High Energy Physics, IISc. She has been a staff associate at ASICTP, a visiting professor at the University of Dortmund, CERN, DESY Hamburg. Most recently, she has been the van der Waals Chair at the University of Amsterdam. She has worked extensively on different aspects of particle phenomenology over the past 3 decades, authoring about 300 research publications, journals, and archive reprints. She also has been an author of graduate level monographs and textbooks on advanced topics for students. She's an elected fellow of all the three national science academies of India, as well as the World Academy of Science. She has won many awards and distinctions, out of which some recent ones are Padma Shri of the Government of India, the Distinguished Alumnus Award of the Indian Institute of Technology, Powai, S.N. Bose Medal of the INSA for Theoretical Physics, Meghnad Saha Award for Physics of the Asiatic Society of India, DST J.C. Bose Fellowship of the Government of India, R.D. Birla Award of the Indian Physics Association. She's worked towards pioneering variety of programs at various fora to raise awareness on the subject of women in science. She's been the chair of INSA and IAS panels for women in science and a member of the same for AASA. She's also the co-author of Leelavati's Daughters, a collection of biographies and essays on women scientists in India. So today she'll be talking about shifting goalposts in pursuit of science. She'll summarize a few things about the current state of particle physics and advancements in that frontier. So let me take this opportunity to thank Rohini ma'am for accepting our invite and taking time out of her busy schedule. So without further delay, the screen is all yours, ma'am.
Thank you very much, all of you, for asking me to talk to you, here to talk to young people. I am trying to, if you can bear with me, share my screen so that you see my talk. Let's see if it works. Yeah, I think it should be fine now. And please confirm to me that you can see my full screen. So,
Yes,
very good. And I thank you all for being here present on a Sunday evening. Somehow with COVID, I think we have lost sense of days of the week and the month. But I am glad to see that you people have enthusiasm and are even not letting this atmosphere dampen your spirits and running things such as science-based. So I'm really glad to be talking to you. So as was told by Parvati, I want to talk about what I call pursuit of science and shifting goalposts. So the plan of my talk is the following. I will begin by giving you some introductory remarks which sort of sets the talk in context. And then I will discuss a few things about what is the current state of particle physics of the subject. Then maybe a very tiny bit as to how did we really arrive here? How did the particle physics community arrive at this understanding of the fundamental building blocks of nature and interactions among them? And then a more important thing, that is what are the next steps? And what I really want to show you or discuss with you and point out to you is that how the results from the Large Hadron Collider have actually shifted the goalposts that we were following for the past. By we, I mean the high energy physics community, theorists, experimentalists, and accelerator physicists. the goalposts that we were looking for or going onwards towards have shifted as a result of the whatever the Large Hadron Collider has presented us with. And then this essentially brings me to my last point, which is one of the major point of my talk, that now there is sort of a time has arrived where the synergy of there is a big synergy of the explorations at the Large Hadron Collider, as well as the explorations of the cosmos, as well as the universe, through a variety of different probes, and that is where I want to end. And the reason I was decided to give this title is to kind of tell you the following, that science, progress in science is not always linear. You know, the community sort of standing on the shoulders of giants, giants like Weinberg or Salam or Glasgow or people like that. The community embarks on theoretical and experimental investigations into the mysteries of nature. I've given you names of only in the context of particle physics. And then we think, we have reached one mountain. We have, what we had been following for decades. The community has been going towards a particular goal. And then the community thinks that we have achieved that goal in our march towards knowledge. We reach the peak, and the vision that is afforded by the high position of this peak of knowledge actually very often raises more questions. And also sometimes it rules out the theories which we thought were going to provide us answers to some fundamental questions about the processes of nature. And these newly acquired heights of knowledge, they show us that there are still new peaks to be conquered, and these had been so far obscured by mist of ignorance. And that's how the journey goes on. And I want to try to take the example of particle physics to sort of establish to you that this is the path through which the science progresses. And this is a combination between theoretical developments and the experimental investigations which go hand in hand. I'm going to take the example, of course, of particle physics to go through this further. So just to sort of set that stage again, I'm sure that you know about different prizes that have been awarded. And in fact, actually, I just realized while looking at the slides that I forgot to add one more, which I will ad-lib just now. So over the last decades, actually, there have been three very important experiments. And these three very important experiments have made historic discoveries which have firmed up our fundamental understanding about how the universe functions and also how it came to being. These are, you will agree, very fundamental questions. The one of them is the discovery of the Higgs boson at the Large Hadron Collider. And this was the last step towards establishing what we call the standard model of particle physics. I will go on and talk about it a little bit more later on. And this was the Physics Nobel Prize of 2013. Then there was this very high precision cosmological measurements with two different satellite-based experiments. One was called WMAP and one was called Planck. And these satellite-based measurements were actually measuring very accurate measurements of the cosmic microwave background radiation, CMBR as it's called. And these measurements actually nailed down what we now know to be the standard model of cosmology. That was the 2018 Breakthrough Prize. Then, of course, there was detection of gravitational waves. This got the Nobel Prize in 2017. And this was the ultimate verification of Einstein's general theory of relativity 100 years after it was postulated. And the least, which I have not written here, but is the Nobel Prize for black hole physics. And again, this was shared between a theoretical physicist, Roger Penrose, and two experimental physicists who actually were able to establish by very accurate measurements that there exists at the center of our galaxy a massive black hole. So these kinds of very precise but very gigantic, rather big experiments actually caught the public imagination, and therefore, even at the level of popular level, the question as to what next has become a topic of a great interest, that now that we have understood such basic things about laws of nature, where do we go next from here? And as I said, I want to take the example of particle physics, and I want to tell you how the results that are obtained are at the LHC, at the Large Hadron Collider, are telling us where to go forward. But how they do that is what I want to tell you. To put it across to you, this is from a magazine called CERN Courier, which is brought out every month from CERN. And I think this was after a few years after the discovery of the Higgs, when the Nobel Prize was given. It's, by the way, now about 10 years, 9 years and some months since the Nobel Prize, the Nobel Prize winning discovery of the Higgs was done. And here is this physicist. She's holding a placard in her hand, and she says, yes, we have discovered what nothingness is made up of. And the other gentleman who is sitting next to her, standing next to her, says, yes, indeed, it's quite something. So this, in some sense, in one picture, gives you the importance of the Higgs discovery. Okay? But, what it did was that it completed the periodic table of particle physics. We all know the periodic table of atomic physics, but I like to call periodic table of particle physics, which is the listing of what we now believe to be the fundamental constituents of matter, as well as the really important and interesting part of the 20th century physics is that not only everything is made up of these fundamental constituents, but everything interacts with everything else essentially only through four fundamental interactions. And these four fundamental interactions are also mediated by particles, which are elementary particles. So the elementary particles are the quarks, the leptons, the force carrier bosons, which are the photons, the W and the Z boson, the gluons. I'm using these names because these names now have become household names, at least for people like you who are in citadels of knowledge, and these are things that come in the usual popular scientific phrase. And of course, the omnipresent Higgs boson. And the discovery of the Higgs boson at the Large Hadron Collider was the last missing entry in the periodic table of particle physics. And this is what it completed, a description of particle physics. And what happened, however, this discovery, it gave us, but after that, the work that was done at the Large Hadron Collider, the continued experiments that were done, actually have presented us with a paradox. What is that paradox? That we have found a Higgs boson, and we call it a light Higgs boson because its mass is very close to the W and the Z boson. I will show you perhaps I forget where I have them or not, but the W and Z boson and the Higgs boson all have about 100 times the mass of the proton, roughly. The exact numbers are there in the table. But because of that, they are all of the same order of magnitude, and therefore we particle physicists like to say that the Higgs boson that we have seen is a light one. I will have more occasion to come back to this again and again. So it looks and smells like what is expected in the standard model of particle physics. What is meant by that is that its strengths of interactions with all the other fundamental particles have been now measured, and they are consistent with what we predict in the standard model of particle physics. So this is the positive part, but at the same time, in all the 10 years since the Higgs boson has been discovered, the LHC experiments haven't given us even a hint of any particle or interaction beyond those of the standard model. Okay, so why should that be worrying us? It should be worrying us because the theoretical physicists, even before the Higgs boson was found, just the same way the model had predicted properties of the Higgs boson, the same similar theoretical considerations had also told us that if the observed Higgs boson is a light one, then there should be, we felt that there are some principles which told us that there must exist particles and interactions beyond the standard model. Now, the Large Hadron Collider has answered very fundamental questions by discovering the Higgs boson, but it has raised new questions because we haven't found any hint of the particles and the interactions that we think must exist to explain why the mass of the observed Higgs boson is what it is. We will have occasion to go more through this, so don't fret if you don't understand much at this point. So, actually, particle physics today finds itself in an extremely peculiar place. I don't know how many of you have ever read Tale of Two Cities, but the first few lines, this is a book written by Charles Dickens, and this was a book written at the time of the French Revolution, and it says, it is the best of the time, it is the worst of the time. It's the best of the times because standard model has been confirmed. And in some sense, it's the worst of the times because since 10 years since the discovery, we haven't even found a hint of the additional physics that we think must exist if our theoretical ideas are right. It's the epoch of belief in the standard model. It is the epoch of incredulity of not finding any new physics. It's the season of light. Indeed, the first Higgs boson event was a Higgs decaying into two photons. And it is the season of darkness because right now the entire particle physics community is grappling with what is dark matter. So it is the spring of hope, but it is the winter of despair because we haven't, or the LHC hasn't given us any glimmer or any hint of anything that is outside the standard model. Oh, sorry, okay. So, LHC results have proved that the very innovative ideas of the past 3 decades that we had actually theoretical physics community had put forward to quote unquote explain why the Higgs boson is light actually don't seem to work. So that just means that the nature is much more subtle than we thought. There are these new peaks that we have to climb, and this makes life more interesting. So this is really what the state of particle physics is. So we can all sort of feel a bit like Lord Kelvin. Again, I don't know how many of you remember, but Kelvin, I think you would remember because that's where the Kelvin scale is named after. And Lord Kelvin made famously the statement at the end of 18th century that there is nothing new to be discovered in physics now. Classical physics can explain everything. All that remains is more and more precise measurements. Of course, there was one cloud on this clear horizon, and that was, of course, the black body radiation. And among those of you who are doing modern physics, they would all know that the entire beginning of the quantum world, the revolution, started because of black body radiation. But let's leave that apart right now. So mere mortals today are sort of, grappling with a similar thought that Lord Kelvin had, that is it that the only thing that remains is more and more precise measurements? That's the question that particle physicists are grappling with right now. In fact, the times of particle physics are sometimes getting discussed even in the New York Times op-eds or Forbes, and here I have produced or reproduced New York Times op-ed by a particle physics colleague. Her name is Dr. Sabine Hosenfelder, and she actually says the future of particle physics is very uncertain because 10 years in, the Large Hadron Collider has failed to deliver the exciting discoveries that the scientists promised. So she has stated exactly the same thing that I stated, namely that the Large Hadron Collider hasn't found evidence for the exciting ideas that the particle theorists had. But however, I think I differ from her in that is not a negative statement, because LHC has not just found the Higgs. It has found the Higgs, and at the same time, when it has not found the things that we were expecting to find, it has actually thrown light on the future steps that we need to take. And before I go and talk about what steps particle physicists are deciding to take in the near future, I would also want to note and tell you that this whole subject or this whole discussion is not just for the benefits of the 10,000 particle physicists alone. Why? That reason is very simple. That would say have been sort of honed fine since the discovery of quantum mechanics, then quantum field theory. We have actually been able to derive sort of a master equation of it all, the one ring to bind them all, so to say, which can describe all the fundamental forces among all the fundamental particles, the three fundamental forces. I should correct myself. Gravitation we still do not have in this framework. But the point is that these laws that we have found, they seem to be functioning at distance scales of Fermis, which is 10 to the minus 13 centimeters, or some of you who are more comfortable with, is 10 to the minus 15 meters, or 10 to the minus 5 angstroms, whatever you like. They seem to be of relevance in addressing things that happen on cosmological timescale. That is, happened at the beginning of the universe, and that happened today at astronomical distances like millions of megaparsecs and beyond. The same laws of particle physics that we study at the Large Hadron Collider or many other experiments before that, and that we continue to study at many particle physics facilities, even our experimental colleagues keep on studying at many particle physics facilities, the same laws have relevance when we try to seek answers to the questions such as, how was everything formed? How did the nucleons form? Can we explain the relative abundance of different elements in the universe? How were the stars and galaxies formed? And believe it or not, answers to these questions, of course, require a lot of classical physics, a lot of astrophysics. But in addition to that, what is the fundamental interaction among the fundamental constituents of nature is an important ingredient to providing answers to all these questions. So therefore, this question is not just of interest to 10,000 particle physicists. What next we need to do is of interest to the entire physics community, astrophysics community, which is in fact looking at solutions of what's happening, about what are the fundamental laws of nature, what are the fundamental laws that govern the functioning of this universe. Here I just begin by showing you one of the events, and it is the Higgs event, where this is, I've taken it from the CMS collaboration, which is the experiment in which Indian colleagues, experimental colleagues actually participate. So it's a two proton and colliding against each other. And this is, of course, the dramatic graphic representation of the event after making precise measurements of the energy and the momenta of the particles that are observed in an event. And this is one event where PP collision produces a Higgs boson, and the Higgs boson decays into two photons. So this discovery actually, I would say, brought CERN, the colliders, and the high energy physics in limelight. Before that, discovery in high energy physics were regularly winning Nobel Prizes. You would be surprised, but in 18 of the years since the beginning of the Nobel Prize, since the start when Nobel Prizes were given, in 18 of those years, they have been given to the discoveries or either the theoretical formulation of the standard model or discoveries which establish the particle content and the interactions of the SL. And let me tell you that I have been extremely miserly in apportioning among the Nobel Prizes which went to standard model. But because of the Higgs discovery, the role of big science came to the forefront, and it also added a sociological dimension to the questions, where does particle physics want to go next? So in particular, there are machines which are called colliders, and these colliders actually helped particle physics community in a big way. The experiments at these colliders helped us in a big way to come at this point. These are gigantic projects No one laboratory or even one country can do it alone. And in fact, evaluation of what might be the best energy, what type of particles should be colliding, all this depends on the physics questions which we want, which the community wants answered, and long periods are required for even these studies. And again, all the three communities which I mentioned earlier, the theorists, the experimentalists, and even the accelerator physicists have to actually work together. Theorists have to first say what kind of measurements we want to make. Experimentalists have to confirm whether these types of measurements can be done at all. And accelerator physicists have to tell whether the kind of beams and the energies and the frequencies of the particle collisions that the theorists and the experimentalists need to test these theories or to learn more about these theories are achievable. Maybe as the time goes along, if I'm left with time, I'll give you a personal connection, story about a personal connection. I doubt I will have that time. All right. So the typical time scale for colliders. For example, the Higgs postulate was in 1968. Machine design was in 1984. Machine building started in 1988, and the experiments happened in 2012. So you realize that a lot of time goes into planning, into building the detectors and the machines. So particle physicists, the community, has to take a hard look as to what steps next, much before those steps are actually taken. So now many people ask this question, and if you look at Sabine Hosenfelder's op-ed that I showed you, that sort of reflects that question. And the question is there life for particle physicists after the Higgs discovery? Yes. We all want to keep our jobs. And actually that is not the case. Particle physicists had started to think about what after Higgs decades ago. And this particular physics is, as I said, looking for particles and interactions beyond standard model, and that we call beyond the standard model, BSM. So SM is the standard model, BSM is beyond standard model. It is just that the last 30-40 years had produced exceedingly wonderful and ideas which had very compelling ideas, but unfortunately so far we don't have any evidence for those big ideas, and that is what I have been trying to tell you for the last half an hour. So before I go and tell you how we will now go ahead in light of what LHC has not discovered, let me also first tell you what are the, I already told you this, that the particle physicists had started looking at what after Higgs decades ago. So what were the reasons for that? So I'm going to actually give you many rational and observational reasons to look for particles and interactions beyond the standard model. I could give you many sort of very aesthetic reasons, but I'm not going to go into those aesthetic reasons because we are scientists. What we do is we try to build theories in which you build a theory, and I'm looking at those theories which are built upon from the hints that we get from experimental observations which we cannot explain. So one of the observational reasons for expecting physics beyond standard model is that there is matter in the universe which does not shine, and that is called the dark matter. I'm going to spend a few minutes or 2 slides onto what is meant by dark matter, but we have very clear evidence that dark matter exists in the universe. Not only that it exists, but it actually forms 27% of the matter of the universe. We have direct evidence for non-zero neutrino masses. This got the Nobel Prize. This has got a Nobel Prize. We actually need why matter dominates over antimatter in the universe, why the matter universe contains around us, and as far as we can see, universe contains only matter. Why is that? We don't understand it, but this is an observation. Then, as I said, we have found a light Higgs boson at a Large Hadron Collider. This is also an observation. We feel the force of gravity. It is one of the 4 fundamental forces, but we do not have a quantum theory of gravity. And this year's Nobel Prize, in some sense, is establishing some predictions of our understanding of gravitation theory. Then there is, last but not the least, which I will not discuss, is the cosmic acceleration. The universe seems to be expanding, that we knew, but apparently the universe seems to be expanding with a ever increasing rate. Now the last 2 points I will not discuss at all in this talk, but in this talk I will really focus on the points that I have written here in blue, and one of them is the dark matter and the other one is the light Higgs boson. All right. So, one of the very appealing and compelling theoretical ideas which people had invented to keep the Higgs light was to have an idea of supersymmetry. And this was suggesting that associated with every particle there should be a supersymmetric partner. And for this theory to solve the problems or the issues that we have to keep the Higgs light, the additional partners should have a mass such that the mass times the c square is less than 1000 GeV. And looking for them at the Large Hadron Collider was one of the ways to probe the BSM ideas. But we have not found any evidence so far at the LHC. I will have you remember that this theory, and this actually is the cover of the textbook which we had written as to how one could look for evidence for supersymmetry, not just at the Large Hadron Collider, but in the context of dark matter experiments. And that is because this theory has ready-made dark matter candidate particles. So what is dark matter? Dark matter is one of the three sort of cosmic connections, and I am going to discuss only two cosmic connections here. So the basic features of, I already told you that the basic features of the three fundamental interactions which we had been talking about actually has bearing on issues which are cosmological, and the contents of our periodic table seem to account only for about 5% of the matter in the universe, and here is the energy budget of the entire universe. 5% is the matter which is there in the periodic table of particle physics, so to say, whereas 27% of the matter is dark matter, which is not luminous, and then there is the 68.3%, which is the dark energy. As I said, I will not discuss this in this talk today, not because I think none of us understand what exactly this is, which makes it very compelling and very interesting subject for investigations, but not much for me to tell you about. So the astrophysical evidence for this dark matter seems to be pretty convincing. I will show you 2-3 slides for that. And I want to make a note here is that the experimental information, okay, that we have got now, which experiments which have been performed to look for this dark matter candidate, and the theoretical understanding as to how this dark matter was produced in the universe, how it came into being, using both these ideas or both these informations, now theorists, and this is not just particle theorists, astrophysicists have come to believe that dark matter requires, as it has been seen and measured, properties that has been measured, requires at least one particle beyond the standard model. There is no particle in the periodic table of particle physics, in the list of fundamental particles of that we have today. There is no particle that we can associate or that we can imagine will be a candidate for the dark matter. But let me tell you that we are able to draw this conclusion only because we have understood perfectly the interactions and measured also equally well the interactions that all the fundamental particles have. Okay, so the astrophysical evidence for dark matter really started from Zwicky, who tried to measure mass of the galaxies from the speed at which galaxies were rotating, and he concluded that if the galaxies had to maintain that, then for the components not to fly away, there must be much more than the visible mass, and that was his argument. But this idea of the dark matter was put forward in very firm footing by Vera Rubin by her measurements. And the sort of, I can give you a sort of what is called a rotational curve, very schematic representation that what you expected, and I will explain on the next slide why we expected this. One expected the rotational velocities of the members of a galaxy as you go further and further away in a galaxy. You expected that the velocities with which they are rotating should go decreasing, but what we found, what Vera Rubin and her collaborators found, is that the velocity doesn't go down with distance, but the rotational velocity seems to continue being large. And this is a very simple example that I have given you. It was first measured for spiral galaxies. These are the most common galaxies that one has. And stars in the galaxies rotate. And one expects that the stars closer to the center will rotate faster. Why do we expect that? You can do a simple calculation. Even a first year physics major should be able to do this calculation, and will find that the velocity, this is a disk, and the velocity of rotation of a star at a distance r will be given by square root of gm by r, where g is the Newton's constant and m is the mass that is enclosed by the orbit. So if f is at a, now f, the far star f is at a distance rf, and nearer star n is at a distance rn. If rf, for example, is 4rn, then this formula will tell us that f should rotate twice as slower as n, and the reality was very different. What does that mean? That means that since Newton's constant does not change as you go away from near to far, clearly the mass that you are enclosing inside the orbit must be changing as you go from f to n to f. But if you look at the luminous mass, which you can extract from looking at the light that is coming out of the galaxy, then you do not understand that you have to basically draw a conclusion that the remaining increased mass is some non-luminous. And you can actually go, if you like, to this particular link which I have given here and watch galaxies actually rotating, and this point comes out very clearly. So these were the measurements that were done by Vera Rubin, and here she saw that the rotational velocities did not go down. And in fact, a much better measurement of a galaxy M33 was done here by astrophysicists and astronomers later. Please note that the velocity is few hundred kilometers per second. It's rather small compared to velocity of light, but this is what you expected from the visible disk. I told you it's a disk, spiral galaxy, and these are the observations from measurements, and you indeed see that this is a very clear evidence for dark matter. Please notice that the distance scales are light years here, so do not think that this is something that you could have guessed by making measurements on the planetary scale. And also these velocities are rather small, which means that the measurements have to be done rather accurately, and that's a different subject by itself about which I don't even know too much. Then at the galaxy cluster level, people had looked at galaxies colliding with each other in a particular cluster called bullet cluster, and what is shown here is in one color is the photograph of the galaxy in an X-ray. In the blue shade is the photograph of the galaxy by gravitational lensing, and indeed, lo and behold, you see that there is much more matter that has gravitational interaction which does not have electromagnetic interaction. And last but not the least, I will not spend any time on this at all, but the cosmic microwave background radiations that I mentioned to you actually confirm a theory of formation of structure in the universe, which requires dark matter to provide the initial potential wells in which the matter fell so as to form different stars and galaxies. Then there is another point which I think, since it's not relevant, but I will still tell you, is that not relevant for my talk here, but I can still mention it. And this has to do with the fact, the baryon-antibaryon or matter-antimatter asymmetry that I told you about, that early universe in principle has to have equal matter and antimatter, and that comes from the laws of electromagnetism and particle physics that we have established to great degree of accuracy on this earth in experiments that are done here. But universe of today seems to have matter and antimatter asymmetry. And as it happens, explanation for this asymmetry in the universe with the known properties of the standard model called CP violation, which you measure in the laboratory, is actually possible with one or two additional postulates, which are also supported in some BSM scenarios. However, a quantitative explanation requires sources of CP violation that are beyond the ones that are present in the standard model, where they have been measured extremely accurately. So this particular BSM physics can also be studied or needs to be studied to understand. This also creates some kind of BSM physics that we need to understand and study for in the collider experiments. So, there were hopes from LHC when we had designed the LHC. This physicist who she's standing there on the horizon. LHC was still on the horizon. And one thought that once you build the LHC, we will find answers to all these questions because the questions were well established by then. And what has happened is as the LHC results have come, we have reached the Higgs peak. We have actually found that the dark matter or baryon asymmetry in the universe or some more finite neutrino masses, those peaks are still further behind. From some distance away, long distance away, we thought that they were all more or less at the same distance, and LHC was going to be able to provide us answers as to what lies at these peaks. But unfortunately, we still find now, after reaching the Higgs peak, that these questions are still something beyond us. Then there are questions in neutrino physics, which I pointed out already, but I think in terms of the time, I will not, maybe let me just say this nonetheless, that this is the table of all the fundamental particles that make matter, the leptons and the quarks. And what I have written here is the masses and their electrical charge. And these are something that I've taken from something called the particle data group table. This means that this has been confirmed by a series of very large number of experiments, and experts, this, get entry into this means that this number is sort of God given. Yes, we know that this is the correct number. And what you notice is that the neutrinos, okay, so the first thing you will notice is that the masses vary in big units. Don't worry about what these units are. I will not discuss this much more, other than telling you that 1 GeV by c square is roughly the mass of the proton. So now you see that the lightest neutrino has a mass of the order of 10 to the minus 9, okay, in these units, whereas the top quark has the mass 173 GeV. So now you see between yourself that there are 11 orders of magnitude between these masses, and we don't understand how, have a basic starting from first principle and understanding why the different particles have such widely different masses. And neutrinos are even funny because all the three neutrinos more or less have very same order, similar order of magnitude masses, whereas the corresponding their partners, the electrons, the muons, and the tau actually seem to differ somewhat more in the masses that they have. But okay, this is what the information we have. Now, basically, therefore, in the next generation of experiments, we would start looking at the universe through different probes. Now, for example, here I want to show you how you can take a picture of the sun through the photons. This is the one that we can normally take, and the picture of the sun through the neutrinos. And then trying to understand whether the two pictures are one and the same actually leads us to give knowledge about the properties of the neutrinos. So there are these big neutrino experiments, IceCube, Dune, INO. There is an Indian neutrino observatory. I hope it comes up soon. Then there are colliders such as the Large Hadron Collider. Then there are optical probes such as the Hanle Optical Telescope, the radio telescope such as the GMRT near Pune, or the Square Kilometer Array, or the most important, the gravitational waves, the LIGO. And now we are going, I think the time has come where all these different probes may be able to work together to give us information about what lies at the heart of the matter and how they interact with each other. So these are the experimental probes. But to understand what these experimental probes are telling us, we are going to have to make progress on the theoretical front. And what are the theoretical challenges? The theoretical challenges are, as I told you, why is the Higgs is as light as it is? That what is understanding the Higgs mass? The Higgs mechanism told me how to understand the masses of the W and the Z boson. And we always say, oh, the Higgs boson gives masses to all the particles. But what gives the Higgs boson its mass? Or understanding this big hierarchy of masses, the top mass to the neutrino mass ratio, I already told you, is like 10 to the 12. Top mass to the electron is 10 to the 6. Top mass to the W is 2. And ratio of top mass to Higgs mass is 1. So these two ratios are of the order 1. This ratio is of 10 to the 6. This ratio is of 10 to the 12. Theoretical understanding of these numbers. And then, as I already mentioned this, that in the history of the universe, okay, how did it all start? The important things there is that this is a picture from I have taken from the web page of something called BICEP2 collaboration, and this is a collaboration of CERN and NASA and BICEP2 together. And this is as we understand today how the universe has developed. And in fact, this is for example the different time scales in the life of a universe. And this is this is the modern universe as we see it now. And this is the period from which the cosmic microwave background radiation came. So when Planck measures cosmic background radiation, it's giving you information about the life in the universe at about 380,000 years. Then at the end of the first 3 minutes, where actually the nuclei were already nuclear matter was formed, and here you see it. Protons were formed at the end of 1 microseconds, so on and so forth. And the BICEP2 kind of experiments are actually looking at the physics that happened maybe here in 10 to the minus 32 seconds. The LHC experiments are actually probing the universe in this time region. Okay, that's where the LHC experiments are. And the gravitational experiments are actually looking and can have a probe into really what happened at the beginning of the universe. So this is where the quantum theory of gravitation also can play. So now the theoretical physicists have a new playground, and these things can perhaps then throw light. For example, gravitational wave measurements can throw light on the correct quantum theory of gravitation. And this is again the same history of the universe. And now I have told you, put the different facilities also. So you see, for example, that the different periods in its universe's life, this inflation, as I said, is actually something that you can probe maybe through gravitational wave experiments. Then this microsecond physics is something that accelerators, the Large Hadron Collider, can probe. Then when the nuclei were formed, life a little after that, at time t equal to 10 to the minus 4 seconds, there you study in the heavy ion collision in the Large Hadron Collider, you study the nuclear fusion and try to produce mini big bangs in the universe. And as you go further and further, the cosmic microwave background radiation is actually giving you information about this epoch in the universe's life, and then in turn also gives you information. It is impacted by structure formation, and that in turn gives you information about dark matter. And indeed, today's expansion is trying to give you information about the dark energy. So this is really what the world is looking like. And LHC actually will contribute to produce the big bangs in the laboratory, as I already told you. LHC will try to detect the dark matter in the LHC experiments. And there are big underground experiments to detect dark matter, which are complementary probes. So these two are going side by side. We need to build collider experiments which will measure the Higgs properties very accurately. And this might give us an answer to the theoretical question as to what gives the Higgs boson light. And this has impacted the planning of future facilities, discussions for which are going all over the world right now, particle physics facilities. We make measurements at the Large Hadron Collider and as well as one more detector at the LHC called LHCb of the particle-antiparticle asymmetry, which might have some answering the puzzle of matter asymmetry. And in fact, some of my own work covers these last 3 points. Of course, I will have no time and I will not discuss this in detail, but a major fraction of the theoretical physics experimental as well as phenomenology community is actually working on these 3 different lines. And we feel that there are maybe 2 ways in which we'll go about it. One is to increase the energy of the colliders and other is to produce new heavy particles. We thought LHC will already help us, and it has only helped us by telling us which of our ideas are not right. But precision measurements of the properties of the known particle is still one more way. So if you cannot have a telescope, you can perhaps have a microscope and you can try to measure things. So accelerators could actually be these telescopes and microscopes. And recent European strategy for high energy physics has been actually discussing the necessary steps, and precision measurements of the Higgs boson and the top quark, as well as precision measurements of the neutrino properties, is what particle physics community will sort of focus on. And people are trying to peep at the BSM land through the Higgs and the top and the neutrino window. And this is a picture of the BSM land 3 in 2015, more or less the day Higgs boson was discovered. In fact, many of these ideas were ruled out, and now as time has gone along, more and more ideas have been shown to be false. And this is how the story is going on, and this is where the physics investigations, both theoretical and experimental, will still continue. And as I said, it will not just be the colliders, but it will be the neutrino experiments, the dark matter experiments, which will join hands with this. Theorists, of course, are trying to still build models which are consistent with non-observation of the BSM physics, and these would be tested in both the dark matter experiments and the neutrino experiments and the collider experiments. And as I already told you, the same experiments will also provide sometimes, possibly, clues to the answers which are cosmological nature, namely the dark matter, the matter-antimatter asymmetry, and maybe dark energy. And the high precision cosmological measurements can constrain the particle theories. The searches at the colliders can prove or disprove a particular particle explanation of the 3 cosmological puzzles. So there are these simultaneous probes into the heart of matter and into laws of everything. Links are there, as I already mentioned to you, even with the gravitational wave detection experiments. So there are surely exciting times ahead. We don't know where the path will go, but the road is long. We may have many miles to go till we reach the goal, and there is a lot of work to do. Thank you very much.
Thank you so much, ma'am, for a very insightful talk. So I guess we can take questions now from the audience.
Yeah, sure. And I will stop sharing my window. Okay?
Sure.
Okay. So
yeah, if the audience have any questions, please put them in the chat box, or please unmute yourself and ask the question.
So we don't see any questions, huh? That doesn't sound so good.
Well, I have a question, ma'am.
Okay. Go ahead.
So yeah, my question is that you mentioned Dr. Sabine Hoselfelder in your talk.
Correct.
Her opinions on math and physics are widely known. So,
yeah.
So she says that physics is getting lost in the search of mathematical beauty.
Yeah.
What is your opinion on that?
As I said, that I mentioned her name because I think her theoretical arguments may be something with which I will have sympathy. Okay, but what I do not have sympathy with is her assertion that the currently going on collider physics experiments are the one that are being planned at the International Linear Collider or any future one next level of E plus E minus collider are not going to provide us with useful information. To some extent, I would agree with her criticism that we need to be very careful about planning for the really huge future collider of 100 TeV based on kind of these aesthetic arguments. And that is why you will notice clearly what I said is that I don't think that we should be basing our discussion about what future facilities we need so much on our aesthetic ideas, which is what she is saying, that we are getting lost in that aesthetics. But there are a lot of issues which are in fact of importance from observational point of view. Okay, I see a question from Anuja Patel in the chat, so which is very similar to what you are asking, Parvati. So I will sort of say this. See, Anuja, I will not say that the solution is always to keep building bigger and bigger particle accelerators, but there are two particle accelerators that are being thought about just now, and they are not necessarily much bigger than what we have built just now. And these are the precision measurements accelerators. One exists already in Japan, and the other one that people are thinking about is in again in Japan or China. And these are the E plus electron positron colliders that I'm thinking about. And I think the case is pretty strong that we need to study the properties of the Higgs particle with great accuracy. And that accuracy could lead us to understand, and that actually shows the potential to understand what lies beyond standard model, or if nothing else, it will actually, to my mind, close the discussion as to whether or not there is any foreseeable energy scale at which physics will exist, which might indicate some deviation from the standard model. If these experiments in the E plus E minus machine actually again show us that such physics scales are way beyond the reach of any collider, then we can actually stop. Okay. In fact, I think these intermediate E plus E minus colliders, to study the Higgs properties in its all intricate details, as well as study the top physics properties in intricate details, are in fact indicated very strongly. And that indication comes from the physics the observations, and not so much from our theoretical considerations of what is the BSM physics that keeps the Higgs light. So Anuja, please let me know in the chat box if you have sort of seen what I'm trying to say. You may not agree with it, but do you see that? Okay, so now there are very many questions. Let me see. First question is from Suvankar Datta, Dr. Suvankar Datta. And he is asking what is the current excitement at LHC. I think the current focus of discussions and discovery at the LHC, LHC is a very interesting machine in the sense that the machine was built to find the Higgs boson. The detectors were built with certain capabilities, knowing what we knew about the properties of the Higgs boson. But these detectors and the methods of experimental analysis are much more capable than just finding the Higgs boson. And a result of that, looking for dark matter, or the same way as I say, closing certain windows of dark matter as not being available or not being realized in nature, is the focus, according to me, of the LHC activities. So right now, LHC has been able to measure the couplings of all the particles with the Higgs boson, including the couplings to the mu. And since it's Suvankar who is asking this question, I can take it further. As you know very well, one of the predictions of the Higgs boson is that its coupling should be proportional to the mass, so that checking this equality in mass all the way down to the muon mass actually constrains any new physics that we may have, And that to me is an important input that the LHC is going to give. So the LHC's current excitement, right now LHC is closed. It will start running again after a year or so. But when it starts running, at that point, it's going to continue its precision measurements of the top and the Higgs physics and dark matter. And that is going to be the focus for all the time. Okay. So now there is a question from, actually things are now moving up much faster. So let me
Yeah, there's
start.
an interesting question from Bhavna.
Yeah, no, I see that now. I can read it. Good. I can read this. So there are two questions. One is from Bhavana and one is from Sonam. So for Sonam, I can quickly answer because it's a rather is a simple question to answer. Is that the next immediate step to keep exploring particle physics right now is actually one which is the continuing experiments at the LHC, and the second is the neutrino experiments, which some of which we are one of which we are planning in India, and that is possible with all the available resources. And as I tried to tell you, it is not just the particle physics experiments like INO. So that, of course, I think is the next thing in the horizon as far as the efforts within India are concerned. But India's participation in LIGO, because even LIGO India, as I tried to tell you, particle physicists are going to have an interest in what LIGO brings out. So therefore, this astroparticle community which can grow, and I think that's something which is very much within our resources. So both INO, continuing presence at LHC, as well as continued presence at an experiment in heavy ion physics at the LHC, as well as B physics studies at in Japan. This is all that particle physics community can do very well with the resources, within the resources, and that is something that would happen right now in the Indian context. Now I want to read a very long question with Bhavana, so give me a minute, Bhavana. Let me read your question. I will read it because I don't know if everybody can see this chat box. So she is saying that could we have some fundamental particles missing, as there seems to be quite a bit large difference between masses from the standard model as we know it now. Like, could there possibly exist some kind of selection which causes only these particles to have measurable detection in our part of the observable universe, and this dark matter could may be more prominent at some other part than that is beyond our range of observation? It's a very good question, Bhavana, because that is what, see, that is the dark matter. I have not given this. Could have given you a talk just on dark matter, but what maybe I will go back to one slide which I had skipped and answer your question. So give me a minute. I will go to, and you didn't go to that slide. What I want to tell you is the following, Bhavana, that at present, about the dark matter, we actually do not have any idea from experiments what its mass should be or what its interactions other than gravitational interactions should be. Because clearly it has gravitational interactions. That's why I spent the time in trying to show you that the existence of dark matter is really inferred from the gravitational interactions that these have. Now, what I did not tell you is that one of the things that you are saying is not quite correct, that you are saying that there exists some kind of selection rule which causes only these particles to have measurable detection, does not allow us to see dark matter. That is not quite correct, because the fact how our understanding how from the early universe dark matter came into being actually posits that the dark matter has to have some interaction with standard model particles. Let me try to give you a very sort of hand-waving description of this. What we do believe right now is that the early universe contained only radiation. And these these radiation meant really photons, and these photons can collide with each other, and in their collisions can in fact produce various standard model particles. The standard model particles can collide in turn and produce the photons back again. So this one would say that the various particles that the photons are capable of producing are actually were in equilibrium in the early universe. But as the universe continued to expand, it became more and more difficult for the particles that were produced from the photon collisions in the forward reactions to find each other again to annihilate and produce radiation. So at a certain point, depending on the strength of the interaction of these particles with the photons, the particles fell out of equilibrium with radiation. Earlier, the rate at which they were produced, the particles were produced, and the rate at which these particle pairs were producing a reaction in the opposite direction were equal. So the number of the whatever species of particle you are thinking of was actually unchanged, and that was in equilibrium. Now, at a point when the reverse reaction became less and less probable, beyond a certain point, a reverse reaction does not take place, as a result of which that particular particle species then now remains in the universe. And that is, we have enough evidence that dark matter is there today. We have enough evidence that the dark matter existed when the structure formation was happening. That is what the CMBR radiations tell you, measurements tell you, which means that if the dark matter had to have been present when the structure formation happened, it must have been produced in the early universe when there was a soup of fundamental particles which were in equilibrium with radiation. And for that to happen, a non-luminous particle must have interactions with the standard model particles. So therefore, we do not know what the strength of that interaction is, and the strength of that interaction and its mass are intricately related to the observed relic density that we see today. So therefore, we do not have enough information about what the mass of the dark matter particle could be. There is a whole wide range. We do not have precise information about what the interaction of this dark matter candidate should be with standard model particles, but we know that they must have some level of interaction to be present to have produced the relic density. And there is this wide range of strength of interaction, wide range of particle masses. Maybe I will try to show you in a few minutes a slide which tells you that from the current experimental measurement, there is an extremely wide range, and we just don't know where the dark matter actually lies. LHC gives you a small window. Dark matter detection experiments give you another small window. And we are simply trying to understand this puzzle through these different measurements. So therefore, that dark universe, so to say, and the dark universe talks to the standard model universe through some mediators is one of the postulate, but it will have to talk through certain mediator. That talking is essential, and that is why we are all perplexed that we do not find the evidence for dark matter in any other place other than its gravitational interaction. So Bhavana, have I explained to some extent your question? Okay. No, with you had second question is that what is it, you have the same question when you replace dark matter with antimatter. That's really not correct. You cannot replace dark matter with antimatter for the simple reason that we have some antimatter. We can create antimatter in the laboratory. We have precise information about the interactions of the antimatter with the universe, with the standard. They are within standard model. Antiparticles are very much a part of the standard model, and they exist in our universe. It's just that the matter that the baryons that make everything are only baryons and not antibaryons. That is, we only have atoms which are made of proton and electrons, and we don't have anti-atoms which are made of antiprotons and positrons. But we know precisely the interactions that is positrons and antiprotons are likely to have. So we know very well that they can indeed talk to our detectors. They simply aren't there. Okay. So I hope you understand my question. My answer. I hope that you understand my answer. Now, there are still many questions, but let me.
So I think Amog has a very similar question to what Bhavna asked. Is your question answered, Amog?
Amog, I hope you're. Yeah. Okay. This is dark energy we have. Okay. I do not want to really discuss dark energy because I think the only evidence for dark energy we have is the expanding universe. Okay, accelerating universe. About dark matter, the reason we are not able to find it is, at least right now, as I tried to explain, I think my question would be clear, answer is clear. But after all the questions are answered, I will go and show you the range of interactions, strengths, and the range of particle masses that we can infer for the dark matter from the current experimental observations of dark matter. And then you can see that this is indeed a very complex area, very complex subject, and we just have these two windows right now, and that is why actually the community is looking at devising newer and newer experiments, okay, in newer and newer mass ranges and newer interaction ranges. So if you give me a minute, Amok and Bhavana, I will show you two plots after we have finished answering the other questions. Now, please tell me in the chat whether this is reasonable. All right. Fine. And Amog, are you also okay with this? Very good. So now let me see what are the other questions. Now Anuja is asking the question, how exactly did people start thinking about interactions in terms of particles? It's a very long question. No, this question will require a rather long answer, but I will give you a short one. And I will tell you where to read things in case you want to look at the history. But you remember, I think all of you have heard about Yukawa's meson. Okay, and this idea initially came from Yukawa, and he kind of posited that the force between a neutron and a proton that holds the neutrons and protons together in a deuteron nucleus, for example, or the force that causes scattering of nuclei or from each other. He was looking at nuclear force, which was holding the nucleus together, and he posited that this might actually be happening as a result of an exchange of a force carrier. And I think this is where the first positing of this idea came. And in fact, Fermi himself mentions these ideas in one of his early papers. So the origin of connection between interaction and force carrier or a particle really started with Yukawa. And as it turned out, when in cosmic ray experiments people found in fact they found a mu particle, they thought that it was Yukawa's particle, but then they realized that this particle doesn't have any strong interactions. And that is when later on people found in about 1947 the pi, which was really Yukawa's meson. So this, if you wish, is the beginning of the idea of interactions in terms of particles. Then the saga actually is a very long saga, and I wouldn't want to take time right now in answering this, but that's really all that I can say. Okay, I have a question from Suvankar where he asks me, what about SUSY? Yes, Suvankar, clearly LHC is focusing on SUSY, and I was not giving the answer in too much detail, but I can tell you maybe again at the end of my discussion, I will come back to this particular question you have asked and will try to give you the answer. Vyom is asking me about quantum gravity. Indeed, there are many theories going around, and if you ask me, I have no idea what has the most potential. I do not work in the area, and I would not be able to give a judgment on these ideas. But that is an exciting area to work on for sure. I mean, that is all I will tell you, Vyom. Then
There's a question by Dr. Nabamita Banerjee.
yeah, I know. So Navamita's question and Suvanka's question, I would try to answer maybe together. Let me just see. Okay, so now I can go to Navamita's question first, and then I will go to the two slides which will answer Bhavana's and your Amog's question. Okay, and which will lead to some answer to a little bit to the answer of Suvankar. So Navamita, indeed the Fenno theory community is really, this is similar to what Suvankar was asking. So the LHC community, that is, there are two parts of the three sections of the Fenno community. The Fenno community, which is interested in flavor problems, that is the understanding the flavor physics, which I already indicated, that we do not understand the big mass hierarchy, and also there is a flavor structure which is extremely intricate, and the beam is on physics. In fact, traditionally we know that the flavor changing neutral currents will have sort of a lot of potential to look for BSM physics. So one part of the community is looking at BSM physics in the context of B physics. Then the remaining, and as I already told you, studying the Higgs properties and looking for dark matter is really the second sector. And the third sector is the heavy ion collisions. Now, the Fano community in any area, whether it is flavor physics, whether it is electroweak physics, is actually moved, and even in the dark matter case, has moved away from models, because the various models that were posited, we didn't find signals in the ranges that LHC could look for the correctness of those models. So people have started doing analysis in what they call effective theories. Mind you, Fermi theory itself was an effective theory, because Fermi theory was a theory of beta decay as a product where the Hamiltonian was simply written as product of currents, and the W was nowhere to be seen. And in some sense, technically, for some of you who understand, it was a theory where the W was integrated out. So now people are looking for analysis of the LHC data in terms of such effective theories where the standard model is augmented by higher dimensional operators which arise from some fundamental theory, and where the heavy particles of that fundamental theory have been integrated out. So looking in the context of effective field theory analysis or simplified model analysis for supersymmetry, for B physics, for Higgs physics, or for dark matter is really what the Fenno community is concentrating on, and that's where a lot of efforts, and actually there are new theoretical challenges how to do maintain gauge invariance, for example, in these simplified effective theory analysis and so on. So I think that is the direction where the theory community is really going forward. The experimental community, of course, is going forward in making precision measurements. And in the heavy ion context, indeed, the theory and the experimental community still has a fair amount of short of ideas. They are not short of issues that they need to look at and study the properties of quark gluon plasma. So that's where the Fenno community is. So I hope, Nabamita, that I have given some answer to your question. Go back to also a little bit to the question that Suvankar is asking, and now I will say this in light of what I have answered to Navamita, that we have kind of people are going away from analysis of the data in terms of a given theory, but I think there is also a need, and that's what is happening also, that you want to scrutinize very carefully the models that you do have, in which you have a lot of belief for very good solid theoretical reasons, and which are, such as supersymmetry or such as sort of small extensions that some of us did recently. So for example, you can look for dark matter through the decays of the Higgs boson into the dark matter particle. That's the invisible Higgs decay. So these are the kinds of things that you can do. Those measurements are happening at LHC. Then now you do, in the framework of a model, calculate the dark matter density in terms of the supersymmetric parameters of the model. And what, for example, we have been able to show recently is that in the mass range where the supersymmetric dark matter particle, the LSP, is very light, between say 5 to 10 GeV, that is a range where the dark matter experiments will not have very strong reach currently. That is also the range where the interactions to give rise to the right relic density. So therefore, one of the ways to either test this hypothesis, either find it or rule it out, is to do the associated phenomenology of the Higgs and searches for the supersymmetric particles. And indeed, the large high energy and high luminosity LHC will be doing that. So this is just an example of the kind of things that LHC will do in the context of supersymmetric theories. So Suvankar, I hope I have been able to give answer to your question, which is somewhat satisfactory. Now let me go and answer the Bhavana's and Amok's question. So you have to bear with me for a minute because I'm going to open a different file because I don't have the pictures I want to show you in this file. So I'll open a different talk I gave some time back and I will just show you the pictures, okay?
Yeah, sure.
And I will then share I'm once again going to share my screen, okay?
Sure.
Okay, so press it now. And I have to share a window. Yeah. Share. Okay. Yeah. So this is one thing I want to, which I had not said, but I will repeat, is that the evidence of dark matter is at all distance scales, going from parsecs to gigaparsecs. This is from the cosmic microwave background radiation. The clusters of galaxies is from bullet clusters, and galaxies is from the rotational velocities. Now I want to show you. Yeah. So now, if you look at the totality of sort of understanding how you get dark matter to be present at the level, at the time in the expansion of the universe, formation of the universe and expansion, at which point in the age of the universe did structure formation take place, just from that, if you're, and that it will provide the right seeds for having structures to be formed, then in fact what happens is that in principle the mass of the dark matter could be anywhere beginning from 10 to the minus 30 GeV to the 6 GeV, except that the particular dark matter candidate, and that it's called something different everywhere, and these are this range here, okay, between 10 to the 0 and 10 to the 3. This is the region for WIMP. So now you see the range of particle masses that could be possibly dark matter could have. Then what happens is that when you calculate the relic density calculation tells you this is the measurement from Planck experiment, and this is the calculation from first principles. And what it does is that it says that this number 3 into 10 to the minus 27 divided by an average velocity, thermal average of the annihilation cross section with velocity in the early universe should be equal to 0.120. This in turn tells you that the cross section times the velocity average cross section should be of the order of 10 to the minus 26 centimeters square. And that's all that you really know. But now you can get the same 10 to the minus 26 centimeters square per cross section by the same sigma annihilation you can get 10 to the minus 26 for a different combination of the coupling of the dark matter and the mass of the dark matter. This essentially decides G square chi over M chi ratio, and that's all that you know. So maybe I have a plot. Let me see. Yeah, here is this plot. So if you try to sort of look at different models, and if you try to say which are the different models which kind of give me the right relic density in the right ballpark for a given mass, these are the same candidates that I wrote in that earlier plot. So that is this huge mass range, 51 orders of magnitude in mass, and you have something like 63 orders of magnitude in cross section, and in this entire range you can get acceptable dark matter candidate, which is consistent with CMBR, which is consistent mainly with rotational curves. And That is where it's very, very difficult to know where to search for dark matter. But when you look in the context of well motivated models like supersymmetry or axion dark matter, then these are well motivated models. And then you can actually have prediction for a phenomenology in the dark matter sector and a prediction for phenomenology at the Large Hadron Collider, at the E plus E minus colliders. And one just tries to look for it in this through these different windows, knowing fully well that we could be wrong. But when we know that if it rules it out, then we are sort of pushed forward to look for newer ideas. And that's exactly was the title of my talk, that pursuit of research always means shifting goalposts. And that's the point that I wanted to make. And I think this picture really tells you how exciting this area is, and at the same time, why is it important that the current experiments also evaluate these regions in the framework of a given model to try and conclusively tell us that these theoretical ideas, which are very compelling otherwise, which are very well motivated, if they do not work, we might even want to understand the reason why they do not work. And that might be a problem that a theorist might want to work on. So, Amog and Bhavana, have you got some answer to your questions? Okay. So, I think I have answered most of the questions. Except a question which was asked by Abhishek Swen. This is, I think this is a bit vague question to answer on a. Okay, I'll read out the question, but I have a feeling that your teachers, such as Navamita or Suvankar, whom I happen to know, and other particle physics teachers would be able to answer this question. He wants to know the difference between weak isospin and weak hypercharge, and which one of them is related to chirality. So the weak isospin is the quantum number that the fermions have. Since you are using these words, I think I can use all the technical words. So these are the quantum numbers that the fermions in the model have. These are the SU2 quantum numbers. They correspond to the SU2 representation to which the fermions belong. And indeed, it has something to do with chirality, because it's only the left-handed fermions which will have weak isospin, and weak hypercharge is the global corresponds to, not global, it corresponds to a U1 symmetry, and it is the charge under the U1 symmetry that the fermions carry, and that symmetry is called the hypercharge symmetry. And SU2L cross U1Y actually then breaks down to U1 electromagnetism, and that is why the electromagnetic charge is a linear sum of the weak hypercharge and the weak isospin. But a more detailed answer, I would request you to ask your teachers, because it requires a slightly more elaborate writing equations and explaining it further. Okay? So, I believe I have answered all the questions.
Yeah, I think that was the last question.
Yes. Okay.
So yes, ma'am. Thank you so much
You're
for
most
this
welcome.
interactive session and very insightful answers.
I am happy.
Thank you.
Okay. I'm happy if I make you people realize that there is still a lot of work to do in particle physics, in astroparticle physics, and also within India, and in theoretical context also. Okay. So that was the purpose. All right. So now
all right.
you can go to your thank you exercise.
Thank you, ma'am. So yeah, before we end this, let's just do the tradition. So I, as the Secretary of Science Council, would so I'll be delivering my thank you note on behalf of the entire Singularity team. So Singularity, first of all, I'm really sorry I cannot turn my video on. I think I have some net issues, but I guess the audio works. So yeah, Singularity, being IISER Bhopal's annual science fest, is celebrated as a fest that promotes curiosity and out of the box thinking. But more importantly, what I think is that it is a fest that has something for everyone. So now I understand that we couldn't hold a lot of events this year, but I hope you really enjoyed all the events that were organized. So, well, an online fest, it's not something that you get to see every day, is it? Or like making a pun on event is not something that happens every day. But this was an experiment for us as well. So I hope you excuse us for any mistakes committed from our part. I don't want to keep you all waiting on a Sunday night, but I need to emphasize the effort and support that I received in making Singularity happen. So I'd like to extend my deepest gratitude to our director, Professor Shiva Umapati, uh, without whom we could not, who has given us unflinching support for the event. We also acknowledge the financial support provided by the Institute in time, despite the pandemic. Thank our Dean of Students Affairs for his constant support throughout, as well as the Students Affairs Office for helping us with any official documents. So a huge thank you to the faculty advisors, Dr. Ramya Sundararaman and Dr. Ranjit Bant, for their unflinching support. So it is truly their support that helped in materializing Singularity to what you all have seen these past few days. Yes, my lovely team. So the Singularity core, each of them have put in their fullest effort, and I really, really appreciate their effort. The online semester isn't really easy on anyone, but these guys have never deterred from the final goal. So this is a huge kudos to my team as well. So organizing an online event doesn't seem easy, but the event coordinators and volunteers have done a really good job. I also thank all the councils as well, the FALC designing team for providing really aesthetic designs, and CNC for all the tech events, as well as the web developers who helped us make the absolutely lovely website that you all have seen. So, and of course, Singularity is all about the participants. Your enthusiasm keeps Singularity alive. And I am so glad the online component hasn't deterred any of your spirits. So thank you all for being part of Singularity. I know the online semester, I mean, all the quizzes and assignments have been a huge burden, but I really, really glad that all of you have shown really a huge enthusiasm towards Singularity. Finally, I would like to say that with or without Singularity, I really, really hope science still prevails. So thank you, everyone, and have a good evening.
Okay, thank you, Parvati, and thank you all of you for asking such nice questions. Have fun and all the best.
Thank you. Thank you so much, ma'am, for joining us.
Okay, bye.
Bye. Good evening, ma'am.